because today we're going to take a look at step functions, which basically is a combination of equations, sort of like we do with piecewise, except with step functions you're going to find out the graph actually looks like you're walking up steps. They're going to be flat, then they go up a little, then they're flat, and they go on that way. So, for instance here, we'll start with a story problem, but nothing too bad. Center High students held a 4-hour fundraising pledge drive. The students organizing the drive counted the money raised at the end of each hour. Okay? So you'll notice here, how much money, and then they get to the end of the hour, then they count it, and then they go to the end of the next hour, then they count it, and then they go, and then they count it. So you'll notice they keep the same amount of money. Now, does that mean they didn't make any money that whole time? No. But since they're only counting at the start of each hour, that's where you're seeing the darkened in circles. That's when the value's changing. So the results are shown in the graph. How much money had the students made after 2 hours? Go to 2, what's my dot on 2? 1,000. Because if I go over to 2, I see there's a dot here, but again, that's open, so I kind of just burn right through it up to here. So $1,000 is the amount of money I'd raised after 2 hours. So then, I keep looking here. How much money did they raise in all? What's the final black dot you see? $1,800. Now again, some of you may be wondering, well, would I add all those black? No, because that's just, I'm counting the total that I have. So what I had the previous hour gets counted in each time. But it's a way we can use this. So if x is the number of hours of the drive that have passed, it's on the x-axis, that makes sense. Then the function f of x, fancy way of saying y, shown by the graph gives the number of dollars raised. Okay, f of x, otherwise known as y. So what is f of 3.5? How much had they made at the 3.5 hour mark? 1,500, because here's 3, here's 4. Here's my 3.5. And if I go up, there's my dot. It's on my 1,500. So we can kind of even use the step function to get some information here. On what interval does f of x, or y, equal 400? Okay. Between 1 and 2, do either of those need an or equals to sign?
Yes.
Which one? First one. Okay, because I've got a closed circle here at 1 and open at 2. So I've got to make sure I get that part. So we'll have that ready. Oh. What's the domain of the function? Least x value to greatest. Nicely done. Okay. So x is between 0 and 4 because it's the least at 0 and the greatest at 4. But I have solid dots at both of those, so I have to have that or equal to line in there. Otherwise, yeah, not too good. What about my range? Least to greatest. Yes, sir.
0 is less than x, which is less than 1800.
Nicely said. We want to be between 0 and 1800 because, again, range is my y values or my f of x values. And so I just go from least to greatest. All right. So then I start looking at it. I'm like, okay, let's see here. What can he throw at us here? Because this doesn't seem too bad to read. These funky symbols that you see here are actually symbols for the same thing, of what's called the greatest integer function. Now this is going to go against everything you've ever learned in rounding. It's called the round down function. And the definition of it and I'll actually write it here, even though I've got it that it's in the book. I want you to be able to see it on here. It's the greatest integer that is less than or equal to x. In other words, any decimal you get rounds down every time. And it's kind of strange to think about, but you'll see why that's necessary in a minute, because that's where our step functions are going to take place. That's where we're going to get our flat horizontal steps. So I start looking down below. I'm like, okay, number 7. F of x is the greatest integer function of x. Find f of -3. Well, you're like, but that's already an integer. Okay, an integer just means I don't have a decimal equivalent. And you're right. So if it's already a whole number, well, no, an integer, whole numbers are positive. If it's an integer, just leave it. But if it's a decimal or a fraction, round down. So what would f of 2.5 be? 2. Ooh, now we're going to see if we're really on it. F of -1.8. Yes. Okay. Now some of you may say, wait a minute, that looks like you're going up. But again, think like you would if you were looking at a number line. If you were looking at a number line and you're at -1.8, remember, you're looking for the lesser value. It's worse to have -2 than it is to have -1. So I've got to come this way. Because we always think of that like rounding up, but it's not when we're in the negatives. What about f of 1/2? 0, because again, if we're at 1/2, we go to the value to the left that's closest, if we were looking at a number line. Which makes the next one a little more interesting. Yep, because if we're at f of -1/2, what's the next number to the left? -1. Because that's the next integer that's less than my x value, less than my value in the parentheses. Okay, so if you're ever in doubt, make yourself a quick number line and then draw it and then go, okay, I want the one to the left, because that'll be the easiest way to get there every time. Now, in some ways, these step functions are going to look a lot like what we just were doing with piecewise, except again, they're going to flatline on us. So the biggest thing to remember when you're trying to do one of these is that, again, f of x equals, these are y values. And these are the restrictions on them. So I start to look and I'm like, okay, so this first one says, my y value is 1, which would be here, if x is between 0 and 1. But again, greater than or equal to 0, but less than 1. So I would have a solid dot at 0, and I'd go till 1, and I'd have an open. And I just color in between, sort of like the ones that we had up in this story problem at the top. Then I'd go to the next one, and I'd say, okay, y equals 2. So let me get up here to 2. Let me zoom a little bit so it's a little easier to see when we get into these bars here. X is greater than or equal to 1. Okay, greater than or equal to x is 1, but less than 2. And you're like, seems like you keep having the one on the left colored in and the one on the right is open. And that's true with step functions. That'll be the case each time. And we just keep going, and we kind of are getting a step going. When my y value is 3, that occurs when x is between 2 and 3. The 2 gets the closed-in dot again because it's or equal to. And we'll make our little barbell of sorts. And then finally, my y value is 4 when x is between 3 and 4. Again, closed-in circle here. Because again, my x value is 3. That x value stays 3. And then we'll go between 3 and 4. So you get these little steps. Now, will they all be that way? Sometimes you'll be given them that way. Sometimes you're just going to be given the greatest integer function. So what we're going to do here is we're going to go, okay, so this integer function 2x. Now, how is this supposed to work? Here's what I want to show you on the calculator, just to let you see. But then I think once you see this, you're going to be like, so I just have to, because there'll be kind of something, I don't want to say magical about it, but yeah, I'm going to use that word. So if you're going to go to the calculator, here's the fun part. All right, let me clear that out. So I've got my 2 there. Well, how do I get the funky little double lines in there? There's a greatest integer function that you can get on your calculator. There's directions for it on the back, but I'll do it with you now here. So I got my 2. I'm going to hit Math. I'm going to arrow over to the numeric one. We've been here before with the absolute value, but now I want number 5, because that stands for the greatest integer function. Once I get there, I'm going to hit Enter. And whatever's inside here, I'm going to put that inside the parentheses. So if I go to graph it, you're like, well, wait a minute, it looks like you've got like connectors going with all of these things. That's because somebody may have messed with my calculator. For me to look see the actual steps, if I hit mode, I do not want connected. I want dot. So if you hit mode, and if you've got a calculator, go down to the connected part and go over to dot, and then graph. Now it'll look more like what we're trying to get done here. So you're like, okay, that's all fine and good, but how do I get values here? Second, graph. Now, let's do some of these for a second. Let's head off in the positive direction and see if we can find a pattern developing here. I just want you to put dots where all these are, filled in dots. So I look up and I'm like, okay, got a dot at 0, 0. We got a dot at 1, 2. I've got a dot at 2, 4. Got a dot at 3, 6. Okay, I'm gonna, oops, Harty. That's not 6, 6. Okay. So, I'm just gonna stop for a second. I got a few dots going. You're like, well, wait a minute. It looks like a line. It does. Then you look a little closer and you're like, well, wait a minute. Intercepts at 0. I'm going up 2 and right 1, up 2 and right 1. It almost looks like it's the equation y equals 2x, or y equals 2x plus 0. That's exactly how step functions work. They're going to work just like graphing a regular line. And here's how it's going to come in, though, because you might say, well, wait, but what about this stuff? It's not just a line. That's true. We make it the step function by going over to the next value and putting an open circle. Okay, they're 1 unit in length. I go over to the next one and I put a circle. And I would do this as far as I'm told for my graph. Now, here's the part that I'm going to have you change slightly on this first one. Notice you have a restriction. You're like, uh-oh. X is greater than or equal to 1, so I come to 1, not the open circle, but here, and it goes until x is less than 4. Open circle on 4, which is as far as we went. So what you see right here would be the actual step function with those restrictions. And it's not often that you're going to get restrictions with a step function. But when you do, those are the little things you have to watch for. That if it's just the less than in this case, that it's open circle. That if it's the greater than or equal to, okay, that we get the closed circle, but we don't go too far. So that's how these are going to work. Now, if there's no restrictions, these are going to be the ones that we love, like the next ones in the group here. Because here, again, I'm going to treat this, and this is what we call our base graph, because there's even ways to do shifts on these. Basically, we're going to graph this like we would graph the line y equals x. Well, if I had the equation y equals x, my intercept would be at 0. And again, any of my initial dots are going to be the colored in ones, the or equal to's. And my slope would be like 1 over 1. And since there's no restriction, I'm going to fill in as far as I can going both directions with filled in dots. Once I have those, my job is to make my steps. And again, they're going to be 1 unit in length. And then I put my open circle at the other end, because you'll notice I get to the end, open circle, shifts up to the closed circle above it. Over, whoops, open, shifts up. And so you don't have any places where there's not a value that's taken. Because every time you get to an open circle, you look above it and there's another closed circle right above. And I did so many this time because, again, there's no restriction. But otherwise, just treat it exactly like you would slope. So if you get y equals 3x, okay, it just means we're going to do what's called step 3, which means the same as my slope being 3 over 1. I don't see any sort of intercept, so I know I'm starting at 0. But now each of my steps are going to get kind of steep, because I'd go up 3 and right 1, up 3 and right 1. Or again, if I can go down and left, that's okay. My steps are always going to be the same width on these, but their steepness can change. And that's all there is to a step function. So if you can graph a normal line, this shouldn't be too shabby. But, once again, certain things we have to be careful of. Now here, if I did it just like a line, you're like, so I just do it like y equals x minus 2. Yes. I go down 2, I put it up. And now the slope, just like number 10, is 1. There's no number in front of x. So up 1 and right 1. Up 1 and right 1. Up and right. Up and right. Up and right. But here's what I would kind of like you to notice once I get my last 2 dots in here. I'm going to go ahead, I'm going to make my bars, but then I want to make a comparison to number 10. I want to make a comparison to our base graph, because I want us to start learning how some of these shifts are actually working. It's good to make this simple, and looking at them like they're just lines is a simple way to look at it. But we need to kind of get the big picture of this, which for these is going to be that we actually just performed a shift. Because once I get that on there, if you look at your original point here, so at 0, I went across here. Here it started right 2 places at 2. My second one was at x equals 1. My second one here is at x equals 3, or shifted to the right 2. So you may occasionally be asked, well, what's just the shift of this? You don't even have to graph it. So it sort of becomes the same thing we had when we were doing the absolute value graphs. Whatever I see in here, you sort of think the opposite. If it's minus, I'm going to shift right. If it's plus in there, I'm going to shift left. And I'll never make you just do one single point. You still could do all of them. But again, understanding the shift is going to be important as we get into some other graphs. And we're going to see all the other shifts on the back here in a minute anyway. So as we flip over, you're like, okay, well now the number's outside. So what's that mean? I'm still going to graph it just like it's a line. This is x plus 1. Okay. My intercept dot goes up 1. And the slope is still 1. So up 1 and right 1. But again, we're going to notice the patterns here as we do this, because that's going to be our key long term. Again, nice for it to be simple now. Better to understand what impact this has later on us. We're always checking where the dot is going to be from where our base graph would be. So here, from our base graph, we basically just shifted everything up 1. So when we're outside the bars, outside our greatest integer function, what this tells me is I go up or down if it's outside, I go left or right if it's inside. Okay? And that's all I'm basically doing on any of these. So you're like, okay, so like here, well, what's going on? Well, I've got the plus 3, so I'm shifting up 3 if I was being asked for a shift. There's my first point, got moved. But then my slope, or my step, is negative 2 over 1. So down 2, right 1, down 2 and right 1, and so on. And again, I can also go, instead of going down 2 and right 1, I can go up 2 and left 1. And again, once I get those set, make sure we get our steps drawn in. Because again, we don't want any gaps anywhere in the problems. And just like anything with slope, the bigger the number out front, the steeper the slope. The smaller the value, the less of a slope that you're going to get, or the less steepness. Here, that first point's going to be shifted up 1 from where it would normally be. And then from there, I'm just going to go up 1 and over 2. Up 1. Now for this one, you may look at it and go, ooh, now wait a minute. If I only put, and let's look at this in the calculator as well. If I'm doing 1/2, am I or am I not going to end up having gaps with this one? So let's clear this out. So we want math. Let's check this out and see what happens. I'm going to use the decimal form here. Oops, not 2. Okay. Oh, I did that again. It says dot. You need to be dot. It does not.
They are dots and are connected. They're just really close together.
Yeah, I was going to say, it's because you've got that. If I changed my window, it would be easier to see on that. But you start to notice, you're like, ooh, now wait a minute. If I look at my chart here, I'm like, okay, when x is 0, my y value is 1. Well, I see that right here. When my x value is 1, okay, it's still 1. So you're like, okay, so 2 goes to 2, 3 goes to 2, and you see the literal steps that go on. So you can, now let's play a game here. What if, instead of counting by ones, so we can take a little more in-depth of a look, we look at every half. Again, it's not changing. So you may get a step in here that's going to be a little bit shorter. But otherwise, I'm just looking to see if there's any other ones that are odd looking. Oh, I see an odd one. I'm going to jump down to 21 here, just a second. She's like, ooh, now we got numbers on the inside and out. So how exactly does this work? Well, you're like, can I just put these together? Technically, you could. You could put those together and treat it like it was x minus 1, but this is a better plan. That plus is going to get me a left shift. The minus outside is going to get me a downshift. So here's how this is going to work. For my first dot, I'm going to go left 1 and down 2, and then do my steps from there. So in this case, slopes back just being 1. And I can go ahead, get all of those in. And have those ready to go. And just in case, again, you either hadn't had a calculator going, or you're like, well, maybe later you decide you're going to look at it calculator-wise, I've got the directions down here for you to be able to get that and look at those. But as usual, we like to find some applications for things where you can see where this actually gets used. So down the bottom there's a story problem. We're just going to set up what this would look like as a piecewise function and kind of go from there. So let's see here. The admission rates at an amusement park are as follows. Children 5 years old and under are free. From 5 up to 12 and including 12 are $5. Children over 12 but up to and including 18 years are $12. And adults are 18. Write a piecewise function that gives the admission price for each age. Oh, gracious. Okay. So it looks like we've got 4 different sections working here. We got children 5 and under. We got 5 to 12. We've got over 12 and up to 18. And we've got adults. Okay. Children 5 and under are free. How much would that be as a price? 0. Okay. So y is going to be 0. If we were to put this in the calculator, it's going to be more like a step. If my x value is what? Less than or equal to 5. 5 years old and under. So then I move to the next one. I go, okay, children over 5 years and up to and including 12 are $5. So I'm like, so we're x is between 5 and 12. Do either of those get the or equal to? 12 does, because it says including. And you're like, all right, let's hit up the next age group. Children 12 years up to and including 18 are $12. Same type of idea, same place the or equal to goes. The or equal to is going to go with my 18, because again it says including. And then finally, we have adults. How am I going to write their inequality? Yep, x is greater than 18. And then if we could graph that if we wanted to, but we don't need to here. We don't have room anyway. So your task, and this is going to be the part that you have to be careful of. This is your homework for this. Now, this is going to be your first assignment in homework check number 4. There is a little bit blending going on in some places on this sheet. You're like, it doesn't look like it. These all look like step functions that I just have to graph. I agree. But when you get to the back, be careful, please. Once you get to the back, I'm starting to blend step functions and absolute value functions. So on 11 through 13 and 17 to 19, you're going to get those V shapes, and you're going to be able to tell me a vertex. If you're not sure, if that's kind of getting a little foggy because it's been a couple of days, pop back and look at those notes back with 2.6 and be like, oh yeah, or maybe even your assignment and go, oh yeah, that's how these work. But so for 11 through 13, 17 to 19, I need a vertex. The other ones are just more step functions for you to work on. And then Monday we can play a little with circles, and then we'll getting ready for the next quiz here. But make sure those last 4 homework assignments are done for the homework check.